Thanks to Squarespace for sponsoring today's video.
Today we're going to look at an important generalization of the Riemann integral, which you learn in a standard calculus class. And that generalization is known as the Riemann-Stieltjes integral. So instead of taking the integral with respect to just the independent variable x, we will indeed evaluate the integral with respect to a function. So let's see the setup that we have. And I want to point out really quickly that this is a non-standard but equivalent formulation of this integral. And it's just easier to work with without getting into things like partitions of intervals and upper and lower integrals and supremums and infimums and stuff like that. Perhaps we'll do like a bigger video later where we look at that kind of stuff. Okay, so let's say we've got functions f and g. And those functions go from the closed interval a, b to r. So they may be defined outside of this closed interval, but for our purposes, in defining this integral, we'll just need them to be defined inside that closed interval. Then we'll define the integral from a to b of f of x dg, so that's like the integral with respect to the function g, as the limit of capital N approaching infinity, of the sum as lowercase n goes from 1 to capital N of f of xn times the quantity g of xn minus g of xn minus 1. And here we're going to take delta x to be b minus a over capital N. So that's like the length of each subinterval. And then we'll take xn to be a plus n times delta x. So what this means is that we're splitting up the interval from a to b into capital N equivalent subintervals. So we've got this kind of thing like maybe a is equal to a0, which is less than x1, which is less than x2, which is less than x3, all the way up. We have xn minus 1, which is less than xn, which is equal to b. So we have that kind of setup. We've made a partition of this interval. It's just, in this case, this partition is into equal subintervals. And now, technically, you would generally see this xn be replaced with like xn star or something, where that's just some point on the subinterval. But since maybe we'll consider only the case when f is continuous, although I won't write that here, we can just take this xn to be anything on that interval, and then since we're taking the limit, everything works out. Okay, so maybe before we get started with our first example, I'd like to point out that if g of x is the identity function, so g of x equals x, then here we get xn minus 1, which is simply delta x by our definitions here. But that would just be the integral of f of x dx over this interval. So this collapses to the normal Riemann integral pretty simply. Okay, so for our first example, we'll ask the question, what happens if if g is differentiable on the interval ab? And this is a logical question because let's look over here. We're taking the difference of g between points that are very, very close together. And that should motivate us to think of this as being similar to the derivative. And in fact, that's exactly what we'll do, is think about this like the derivative and apply something called the mean value theorem. So let's write that down. So by the mean value theorem, so that should be on the screen right now if you'd like to check it out. We have there is a point which I'll call xn star on the open interval from xn minus 1 to xn, such that g prime of xn star equals g of xn minus g of xn minus 1 over xn minus 1. So something like that. And let's recall that the mean value theorem says that if you've got a continuous differentiable function, there's always a place where the slope of the tangent line is equal to the slope of the secant line. In other words, the instantaneous rate of change is equal to the average rate of change. So that's what's going on here. But now let's note that this denominator is simply equal to delta x. So we can rearrange things here to see that g of xn minus g of xn minus 1 is in fact g prime of xn star times delta x. Okay, so that's cool. So let's see what that leads this integral to collapse to. So we'll have the integral from a to b of f of x dg is equal to the limit as capital N goes to infinity. So at this stage, I'm just copying some stuff over. Then we have our sum, and then we have f of xn, and then g of xn star, sorry, that should be g prime of xn star, and then delta x. Okay, nice. But notice that looks just like the normal Riemann integral, so the integral with respect to x, but instead of taking the integral of f, we're taking the integral of the product of these functions f and g prime. And so, by that observation, we have this is simply equal to the integral from a to b of f of x times g prime of x dx. So we're left with something like that. Okay, well, that's what happens if g is differentiable. Well, what if it's not differentiable? Then you probably have to look at all classes of functions of g on their own, and we'll exhibit some of this behavior with a certain example involving one of my favorite functions.
Before we continue, I'd like to thank today's sponsor, Squarespace. Squarespace is a service that takes the hassle out of creating a website. You don't have to be a programmer or a graphic designer to have a professional-looking website. Because of their support, I can dedicate all of my spare time to doing the things that I love, and I have more time to focus on my mathematical research. With Squarespace, you too can focus on what's important to you and leave the technical stuff to them. The new Fluid engine gives you complete control over the structure of your website. The simple drag and drop action will get your site online quickly, and access to analytics will help you tailor your content to your audience. I use Squarespace for my website, and I find it easy to use with plenty of integrations. They even have a plugin for LaTeX that allows me to include equations on my website very easily. Whether you need a place to sell your merch or show your art, Squarespace has the tools you need to keep your website modern and easy to use. Give Squarespace a try by going to squarespace.com/MichaelPenn to save 10% off your first purchase of a website or a domain using code MichaelPenn. Thanks again to Squarespace for sponsoring today's video.
So like I said before, we're going to explore this non-differentiable case for g by looking at integration with respect to one of my favorite functions, the floor function. So this thing isn't even continuous. So we're going to maybe get a closed form for the integral from a to b of f of x d floor of x. And just for the sake of keeping everything nice, we'll take a and b to be integers. Now, before we jump into like a derivation of a closed form of this, let's play around a little bit with what's going on here. And in order to do that, let's sketch out the floor function, and then in turn, think about what's happening with this g of xn minus g of xn minus 1 when g is the floor function. So let's say that a is right here, so that's an integer, recall, and then here would be a plus 1, here would be a plus 2, all the way up here would be b, and right before that would be b minus 1, but I think that's kind of enough to have on the board to get an idea for what's going on. Okay, so now let's bring a right here, a plus 1 up here, and then a plus 2 up here, and get the graph going. So by the definition of the floor function, we know that the floor of a is equal to a, given that a is an integer. But anything between a and a plus 1 will floor back to a, except for a plus 1, which its floor is equal to a plus 1. So we get this step function. So I'll draw the step function like this, and let's notice I fill in the dot on the left and I keep the dot on the right open. So we've got something going on like that. Okay, so now let's say we had our x in, or maybe we'll call it xi right here, and our xi plus 1 straddles on the other side of this. Or maybe let's write this as xi minus 1 and then xi. So something like that. Well, given that setup, let's notice that we indeed have the floor of xi is equal to a plus 1, whereas the floor of xi minus 1 is equal to a. So floor of xi is a plus 1, floor of xi minus 1 is a, just given the behavior of the step function here. So under this setup, we would have the floor of xi minus the floor of xi minus 1 would be equal to 1. And in fact, this kind of behavior is going to always occur when our interval straddles between these two integers, or between any two integers. So if xi minus 1 is smaller than a certain integer and xi is equal to or larger than that certain integer, then we get this difference of 1. Well, what happens if instead of straddling, they lie in between the same two integers? Well, in that case, we could maybe highlight that by looking at xj minus 1 here and xj right here. But notice those both lie on this portion of the floor function where we just have a horizontal line. So in this case, we would have the floor of xj minus 1 equals the floor of xj, which is equal to a plus 2, based off our picture. But that tells us that we have xj taking the floor minus xj minus 1 taking the floor is in fact equal to 0. So we get the difference is equal to 0. So just to reiterate what's going on here, if our certain partition straddles an integer, we get a difference of 1 for this floor function. And then if they lie in between the same two integers, then we get a difference of 0. So that means in practice, we should have this sum right here collapse quite a bit, because this object right here will be most of the time equal to 0. Okay, so let's keep that intuition in mind, and now we'll go towards a closed form of this. Okay, so now let's keep that in mind, and let's note that maybe we would like to find values of I here, or values of n, whatever index you're using, so that we land exactly on an integer or as close to an integer as possible. So let's see what it would take for that to happen. Let's see what it would take to land on a plus 1. So what if we wanted x sub I, or maybe we'll call it x sub n, as that's our index over here, and we want that to be equal to a plus 1. But then using our formula down here for x sub n, we have a plus n times delta x equals a plus 1, which means we'll need n times delta x, which is b minus a over capital N, to be equal to 1. Which means, in fact, we'll need n to be equal to capital N over b minus a. Okay, so that in itself is pretty interesting, because most of the time this is not an integer. Maybe I really shouldn't say most of the time, but in general, this is not an integer. Well, really not a positive integer. But if instead we require the number of subintervals to be not super general like this capital N, but we require it to be an integer multiple of this difference, then perhaps we can get some simplification. And that's exactly what we'll do as we move forward. We just got done with some exploration as to how this problem might go, or in other words, some tricks that might be useful for getting a closed form of this. And one of them was to take the number of subintervals here to be a multiple of b minus a, or the length of the interval. Well, in order to do that, I'd like to introduce some notation. So let's maybe set m equal to b minus a, and let's notice that this is in fact a natural number. And I'll just maybe require a and b to be non-equal, so we know that this is a positive integer, not just a non-negative integer. And one more thing that we want to do is use m times capital N subintervals. Okay, so this introduction of notation as well as this requirement for the number of subintervals is going to make our calculation quite a bit easier. Okay, so now let's build these parts out over here. So in this case, we have delta x is equal to b minus a over the number of subintervals, which is in this case m times capital N, but that's going to simplify to 1 over capital N based off of our choices over there. So to reiterate, delta x is 1 over capital N. And then from that, we can look at x sub n, and that will be a plus little n times delta x, so that's going to be little n over capital N. Okay, so let's keep that in mind. This is going to be something important to use. This x sub n is a plus lowercase n over uppercase n. And then we need to do another little calculation as well. So let's maybe put this under something that we observe. So let's observe that if we want x sub n to be equal to a plus k, where k goes from 0 to m, so that means x sub n is equal to a plus 1, a plus 2, a plus 3, all the way up to a plus m, which is equal to b, then that will simplify to n being equal to k times capital N. So I'll let you guys do the little simplification that gets us there. That's not so tricky. Great. So if little n is equal to capital N, we get a plus 1. If little n is equal to 2 times capital N, we get a plus 2, and so on and so forth. And this may seem a little bit problematic because here we're just going up to capital N, but recall here we're using m times capital N subintervals. Okay, so now we're ready to make our calculation. So let's bring this down. We have the integral from a to b of f of x d floor of x is equal to still the limit as capital N goes to 0, but now we'll have the sum as lowercase n goes from 1 to m times capital N. That's where we're using our number of subintervals. And then we have f of xn, and then the floor of xn minus the floor of xn minus 1. So we're left with something like that. And now we're going to split this up into parts that straddle across integers and portions that remain between two integers. And I'm going to do that by taking this sum right here and expanding it. And then we'll get rid of this expansion and write it a little bit more succinctly. So this is going to be equal to the sum as lowercase n goes from 1 to capital N minus 1 plus the case when lowercase n equals capital N. So I'm splitting this up into these terms right here, these terms right here, and these terms right here will have xn's that lie between a and a plus 1, but not equal to a plus 1, whereas this is the case when xn is equal to a plus 1. And then we'll go to the next bit. So then we'll have the sum as n goes from capital N plus 1 up to 2 times capital N minus 1 plus the case when n is equal to 2 times capital N. And then we'll continue this process, and we'll end with n is equal to m minus 1 times n plus 1 up to m times n minus 1 plus the case when n is equal to m times capital N. So not only did we break this into m pieces, but after breaking it into m pieces, we took the top term off of each of those sums. So that's what's going on here. But let's notice that I can collect all this together into the sum as k goes from 1 to m of the sum as n goes from k minus 1 times n plus 1 up to kn minus 1 plus the case when lowercase n equals k times n. So that's bringing all that stuff together. Okay, so now that we've done that scratch calculation, let's put it all together into something a little bit more formal. So this is a more formal version of what we sketched out on the last board. Now we're ready to simplify it quite a bit. So let's notice in this interval right here, by our construction, we have xn minus 1 and xn are on the following open interval. And that open interval is from a plus k minus 1 times n to a plus k minus 1 times n plus 1. But that's just two consecutive integers. And if we wanted to write that like integers, then we might call this first one the integer c, and this second one would be the integer c plus 1. But if those two numbers lie on an open interval constructed from two integers, then that means the floor of both of them is equal to c. So let's write that in here. The floor of this is c, and the floor of this is also c. But clearly, if you subtract c from itself, you get 0. So that means this big sum right here just cancels all the way down to 0. So that's pretty nice. And then we're just left with this leftover term. So let's also note that by our construction, this xkn is equal to a plus k, whereas this xkn minus 1 is a plus k minus 1 over capital N. But then let's notice that if we floor this one, so let's say this blue arrow is taking the floor, we simply get a plus k. But if we floor this one, we get a plus k minus 1. As a plus k is an integer, and this is just below that integer. Remember, we want to think about capital N as being quite large, so it'll be below a plus k, but it won't be below a plus k minus 1. But notice when we take the difference of these two, we exactly get the number 1. So here, this simplifies to the number 1. Okay, great. And now let's see what we have. So we'll have the limit as capital N goes to infinity, and then the sum as k goes from 1 to m of f of x kn, but remember kn was just a plus k, so that's going to be f of a plus k. So something like that. But after all of our simplification, this object no longer depends on capital N. So that means we don't need this limit here anymore. We're taking the limit of something which is indeed a constant with respect to the limiting variable. So we just get the sum as k goes from 1 to m of f of a plus k. But expanding that out, that's f of a plus 1 plus f of a plus 2, all the way up to f of a plus m, but f of a plus m is equal to b based off of our notation up there. So we could perhaps rewrite this as the sum as little n goes from a plus 1 up to b of f of n. Okay, so let's underline the starting point here and the ending point here, and notice that taking this Riemann-Stieltjes integral with respect to the floor function is some sort of path between what is generally a continuous question, taking an integral, to a discrete question, which is taking a sum. So this is maybe a further link between the notion of an integral and a sum. In fact, I've done other videos on the channel on the links between integrals and sums. One involves using the fundamental theorem of discrete calculus to calculate a sum. So maybe that should be on the screen right now if you'd like to check it out. And that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.